With me tonight is Dr. Andy Yu. He actually got his PhD while using VSim, and he now works with us as an application engineer. So on that note, Andy, welcome. I pass over to you.
All right, can you hear me well? All right. So this webinar is intended to give us an overview of VSim as a whole and the new features of VSim 12. So we have 2 more days of technical presentations after today, starting 9 a.m. Mountain Time tomorrow morning. So this is the overview of the VSim. So as many of you know, TechX was founded in 1994 by Dr. John Carey and colleagues. So as old as me is a company. So that's quite some time, 20-something years old. And the company's vision is to use the latest advances in physics to solve complex and real-world problems. And VSim is a very widely cited software, simulation software. And this chart you see is cited 824 times. That is not the total citation of VSim. That is the citation number on one single paper published in 2004, which introduced VSim for the first time. And if you are interested in seeing more publications, you can go to this website here. And there are upwards of several hundred publications using VSim you can find there. And there is a whole wealth of information there for anyone who is interested. So our company, TechX, have a focus on plasma simulation. And I would even be bold enough to say that we are currently the leader in plasma simulation. Many people can do electromagnetics. Many people can do ordinary particles. Not a lot of people can do plasmas. So our primary product is VSim, as all of you are here for. And Vorpal is a computational engine behind VSim. So let's go to the next slide. So what is VSim? So VSim have multiple physics solvers. We solve fields, that's electromagnetics and fluid. We solve particles that include charged particles and like electrons and ions, and it also includes neutral particles as well. And we solve collisions, that is collisions and reactions, that is the interaction between particles, such as ionization, such as the combination, such as excitation of that. And we solve all of these in self-consistent ways. So we solve all of them simultaneously, and the result can be trusted and is robust. So we have many different solvers. The main solver we use is FDTD, that's finite difference time domain. So VSim is a time domain solver. And the finite difference is a very, very robust algorithm. It is simple in principle, but it's not really that simple to implement. There are many nuance there. And we also have implicit solvers like Poisson solvers and inductive solvers. We have Monte Carlo collision, and we have particle motion. That is our PIC solver. And all of those, as I have mentioned, are one unified self-consistent whole. So one main advantage of VSim is that if you know anything about finite difference solvers, is that the simulation grid has to align with whatever coordinate system you're using. So in Cartesian coordinates, you have this problem of stair stepping. So basically, if your geometry only partially fills a cell, with stair stepping, you either count the cell as entirely filled or entirely unfilled or empty. But VSim have a conformal surface representation with its cut cell algorithms. And we are able to have a much finer resolution of the simulated geometry and hence improve accuracy. And VSim is a massively parallel algorithm. It's a massively parallel solver. So we are capable of handling very large problems on supercomputers. And we have very good parallel scaling up to tens of thousands of cores, and these are the tested and confirmed numbers. So VSim is currently divided into 4 different packages depending on their capabilities. So our flagship product currently is VSim PD. And this product is, PD stands for plasma discharge. And this product is intended to solve problems such as wafer fabrication, plasma processing, plasma thrusters, neutron generators, and ion sources. So this package is great for anyone who is doing reactions, plasma chemistry, and especially processing. We will talk about that more a little bit later. We also have VSim EM, stand for electromagnetics. So these applications, including your ordinary applications such as antennas, phased arrays, materials, electromagnetic waves in materials, and more importantly, lately photonics, we are able to go to very, very high frequencies while maintaining stability. And we also have VSim VE. VE stands for vacuum electronics. This package used to be called MD. We changed the name of that in this release to align with industry conventions. So these questions are klystrons, magnetrons, TWTs, and multipacking. Basically, when you are doing anything that when you are doing applications that has anything to do with beam field interactions. And we also, our first package is VSim PA. PA stands for plasma acceleration. And as the name indicates, these are for accelerators and plasma research. This is a more science-focused packages, while PD, EM, VE are what I would consider more engineering-focused packages. So VSim is ideal for physical simulations of plasmas. As I have mentioned, I believe we are the leader in this field currently. So we can simulate particle capture on surfaces, collisional processes, sputtering, secondary yield, and sheath dynamics. So a very wide array of applications. And I would mention here is what VSim does not deal with currently is anything mechanical. That includes thermodynamics, that includes material stress. We don't have anything to do with that. So we take care of the plasma interactions and anything that you would consider electrical. So VSim is also capable of solving computationally intensive electromagnetic problems. And as I have mentioned, we have conformal PECs and dielectric algorithms. Conformal means we are able to go into the subcell level and take care of geometry, complex geometries within the cell. So we can do problems, as you can see here. On the bottom left corner is a problem of a waveguide solution, MOS solution, and next to that is a phase antenna, and next to that is the traveling wave tube. So a very, very wide array of problems that involves either fields alone or field and particles together. So what is new in VSim12? VSim12 has the big improvement is in the plasma discharge arena. So we added a flexible reactions framework, and we also added a lot of very widely requested examples such as Magnetron sputtering, and we added some neutral fluid, and we also added a lot of what I would call quality of life improvements, such as parameter scans, time averaging analyzer. So I will talk about some of that in more detail. And if you are already a current user of VSim, you will be receiving a detailed release note on all the improvements that come with this iteration of the software. So we have an improved reactions framework. Reaction framework now features unlimited number of reactants on products. I know more than one person already that would really appreciate this function, this feature here. And reactions can now be localized to geometric surfaces. We have added new reaction diagnostic tools that improved understanding. And also, now collisional cross-section files can now be imported from this new formats. And the image you'll see on the right is electron-argon impact ionization. The color you are seeing are the ionization rates. So the hotter the color, the higher the rate. So as you can see, in this case, there is a very high rate near the input, near the throat of the chamber, and also when the gas is just entering the chamber. So this is a quality of life improvement. A lot of our competitors already have this, and we are a little bit late, but it's finally here. So now you can scan multiple parameters. You can do parameter scans with VSim natively in VSim Composer. So this allows you to run several simulations at the same time. And this is highly helpful if you are doing any kind of iterative solution, or if you are unsure about your design parameter and you just want to try out a bunch of them. And one of the biggest use for this is that one of the biggest thing about this is if you are dealing with very large problems, and sometimes, at least for me, one issue I used to run into is that I start a simulation in the day, and then the simulation will be finishing in the middle of the night when I'm asleep. And I wouldn't have time to immediately do the next iteration. And in that case, I waste half day of my computational time on my server. So this tool helps you solve that problem, that you can just set up, especially when working with very large problems, you can set up all of those parameter scans and just forget about it. Then when you walk back sometime later, it's all done for you, and you can begin to review the results. And we will have a demo showing this parameter scan working later in this presentation. And we have added in external circuit models in VSim, and is now available in Visual Setup. It's much easier to use, and currently we only have resistive models. And this feature is critical for Magnetron sputtering examples that will be shown later this week. And another feature we have embedded into VSim Composer is now you are able to make simulation videos natively in VSim Composer. So this allows you to make an animation based on your simulation results. So it's sequentially attached together your dumps, and it will give you a movie. So a new analyzer that is added is you can now do time averaging natively in VSim. I know a lot of our power users are probably already doing this in Python in post-processing, but now you can do this natively in VSim, and it's much faster than compared to if you have to export your data first, read it in Python, and write your own script to do that. Now you can do that natively in VSim. And we have added this new example for Magnetron sputtering. I can tell you this is one of the most widely requested examples or applications VSim gets these days. Everybody seems to be interested in Magnetron sputtering, and we finally have an example for that. So VSim simulations can now be used to determine the optimal setup conditions for Magnetron sputtering, but users will need to provide the magnetic field data. External circuit model is critical for obtaining steady state. And if you are interested in working with this type of applications, we strongly encourage you to work with a TechX application engineer. And I would inform you that we have an entire technical presentation on this very topic by Dr. Daniel Min later this week, Thursday at 10 a.m. Mountain Time. And it's titled Using VSim to Optimize Your Magnetron Sputtering Setup. So for anyone who is interested, go to that presentation. And we have added another new example that is Townsend discharge with parameter scans. So now you can use the parameter scan feature to directly obtain the Townsend coefficient of a setup. So in this case, we will do this example as a little demo. We'll now go into the physics of this whole thing. What you need to know is that Townsend is basically an avalanche type of behavior, and is originally it's a plasma process that amplifies current. So there is this very old paper published in 1964 by Channon and Rourke. And I believe those are two engineers at Honeywell, and they have determined that for this set of parameters you see here, we should be able to get a Townsend coefficient of 1.3. So the Townsend coefficient here is alpha, and P naught is the pressure. So this number is experimentally determined. And now what I'm going to show you is how you can use VSim to produce this number. So with that, let me stop my share, and I will pull up a VSim. I will pull up VSim12. Here. Hopefully everyone can see this. If not, let me know. So this is the basic interface of VSim12. As you can see, it's very similar to VSim11, other than this tab here. Now you have a design tab, and this is now, or this is where the parameter scan feature resides currently. And in future versions, we are going to have more functionalities here, but right here we have parameter scan. So to access this Townsend example, simply go to File, go to New, From Example, This Townsend example is under plasma discharge process Townsend. So here I already have one opened. When you open it, you are going to see here. So this setup is relatively simple, as you can see from that example image. The setup is a parallel plate. It's a parallel plate with a voltage in between, and in this case, there's also helium in between. So in this case, when you set it up in VSim, you don't need to include explicit geometries. You can simply define a boundary as your geometry. So I won't go over the setup. If you are interested in how this model actually works, or if you are interested in exploring the background physics, I will point you to a really helpful documentation. So for all of these examples, you see under every category, we have extensive documentations for every example we have. And to access that, you simply go to help, click on that, and that is going to pull up VSim documentation. And to access this example, go to VSim examples. This example is under plasma discharge, or you can simply search for Townsend or TOW. And here you can pull out the problem description, and this documentation will run you through the entire example, including the background physics. So in this case, what are we trying to do? We're trying to solve an equation like this here. Let me pull up a pen. We're essentially trying to solve this equation here. So we want to solve for alpha. We want to solve for alpha. We have an input current, and we have an output. We can simulate the output current, and we can control x minus x naught, which is the separation. But in this case, we scan the voltage instead, which gives the equivalent effect. So we want to have an array of input current, then we simulate an array of output current based on our different voltages. And by that, we can calculate what this alpha value is, which we have experimental data for. So to do that, let's go back to my example. And typically, at this point, after setting up your example, you will go to run. And when you click run here, it will run whatever your setup is here. But if you want to run multiple setups at the same time, now you go to the design tab, and you can, here is your parameter scan interface. So in this case, you give it a name. I mentioned I want to have the equivalent effect of different separations by scanning the voltage. You can scan other things too, like if you want to scan pressure, you can. You can even scan more than one parameters at the same time. And that will give you a matrix of all combinations of whatever number of parameters you input. So if you have 3 different values for parameter A and 3 different values for parameter B, you will have 9 different parameter scans, 9 different cases. In this case, we only scanned one single parameter. And we want, this is a voltage between the parallel plate. And to do the scan, you can either do, you can scan a list of values. In this case, you will be manually inputting every value you want calculated for this parameter voltage difference. Or you can scan a range. In this case, you tell VSim what is the minimum value, what is the maximum value, what is the number of points you want to scan, and whether you want to do a log scan. You can even do random values if you just want to try random things. And So it's very conveniently set up. And also under run settings, VSim will default to whatever it thinks is the best way, is the best combination to utilize all your hardwares, and that is all the core combination. So in this case, I have 7 runs, and I have 64 cores on my machine. So at the bottom, you can see I will have 7 concurrent parallel runs with 9 cores each. So 7, that's 63 cores running at the same time, and they will all be executing at the same time. If you don't like this allocation and you would like to do it manually, simply unclick default, and now you can tell VSim how many cores you want to use for each run, and how many concurrent run you have to do. This will be useful if you are using a shared server and don't want to simply max out all the resource on that server. So in this case, I already, after this setup, simply click run. And in this case, I already did the run. This run actually go really quickly. On this machine, it's finished under about 10 minutes for all 7 cases. So after that, after you get all of those data, and mind you, what you are getting is, you know what I naught is, you know what x minus x0 is, this is your v, and you are simulating what ix is, and that's the output. So now what you have, if you inputted 7 I naught, and you inputted 7 x minus x naught, that's your v, and you are scanning a lot of different values for I naught, and you are getting a lot of values for I. And now you have a lot of data that enables you to compute what alpha is. But in this case, you can obviously compute alpha on your own with post-processing in Python. But in this case, we actually have an analyzer that is built into VSim12 that automates this process. And this analyzer is simply called Scan Analyzer Townsend. And after you input your desired parameters, and you tell the analyzer which parameter did you scan, in this case is the voltage sweep, and you have 7 different cases. Now if we click analyze, now it's telling me that my alpha over P naught is about 1.3, which is the experimentally confirmed value here. And if you want to see the original paper, simply Google this name, you will see that paper. It's a very well-known paper. So that is parameter scan in VSim12. It's mostly a quality of life improvements, but a very important one. And I will stop sharing this screen, and let's go back to the presentation. All right, so we just went through this. And that is all I have for you for this webinar, is a overview of VSim12 and overview of the new features. I didn't touch on everything. As I said, you are going to get a release note, and I'm pretty sure you're going to find it interesting. So here are some of the schedules for our technical presentation that's on tomorrow and the day after. Starting at 9 a.m. tomorrow with my presentation, I will be doing a presentation on how you can explore the fundamental physics of cavity magnetrons with VSim. And we have all those other interesting presentations, including the magnetron sputtering one. And with that, I will take any questions you may have.
There is the little Q&A box on the bottom of your screen where you can actually type in questions. So if you have anything for Andy, go ahead and type that in. We hope to have VSim12 Andy tomorrow or Thursday, right? I thought,
Right, or
I have tomorrow morning, but I heard you say.
within this week, how about that?
Yep, we want to make sure it's exactly where we want it to be. So if you are interested in evaluating VSim12, send us an email to sales@txcorp.com. And as soon as it's ready, we will get it sent off to you. Make sure to tell us the operating system of your computer. Okay. Well, I think, Andy, I don't think we have any questions tonight. And so I think we can go ahead and wrap up.
All right, great.
Thank you so much, everyone, for joining us tonight. And we hope to see you all tomorrow at TWIS.
9 a.m. Mountain.
9 a.m.
Yep. All right. I will stop sharing. All right, I think we're done here.